Hello, I'm Robin Cole, and welcome to the Satellite Image Deep Learning Podcast. In this episode, I caught up with Yotam Azriel to learn about interpretable deep learning. Deep learning models are often criticized for being black box due to their complex architectures and large number of parameters. Model interpretability is crucial as it enables stakeholders to make informed decisions based on insights into how predictions were made. I think this is an important topic, and I learned a lot about the sophisticated techniques and engineering required to develop a platform for model interpretability. I hope you enjoy this episode. Hi, Yotam. Welcome to the podcast.
Hi, Robin. Thanks for being here.
Fantastic. Let's begin with where you work and what you do.
Well, I'm CTO and co-founder in TensorLeap. It's a small startup who develops applied explainability platform for neural networks, trying to add some observability, explainability to the development processes and production monitoring
Right.
area.
Fantastic. And at a high level, what are the techniques for interpretability?
Oh, well, so we can split it to global and local explainability, and for each one of them, we'll have different sets of techniques. We are around for 4 years, and we invested a lot of building the paradigm and the infrastructure that can handle those different kind of needs.
Mm-hmm.
Uh, and it also depends on the reasons you want to get explainability, and this is why we call it applied explainability. We're trying to say you can utilize those insights if you're building the explainability in a way that you can query those insights and automate different workflows in the development processes or the production monitoring area.
Right.
So where we'll try to detect, for example, edge cases that tending to fail or area that the model might overfit on certain features. If we'd like to maintain production environment many time, it'll be mostly different techniques on the embedding space to distill embedding space from different layers that can capture certain essence and describe well a small population, and creating different, kinds of signatures of model behaviors from within the features
Mm-hmm.
that you can utilize it on a big scale.
Right.
Uh, on the other hand, when you're speaking about local explainability, maybe people will go towards those direction when they try to understand why the model behave in certain cases very deeply, why it predict a certain class, why it why the uncertainty is so high on in few samples.
Mm-hmm.
So uh, in those cases, we'll usually apply different kind of techniques like RADCOM and all those family of techniques.
Mm-hmm.
Why we did like got it, a few steps further. For example, recursively derivating those features that impacting the features backwards and backwards and backwards in order to explain how
Right.
the features emerge. Like,
Right. And imagine in let's say you're talking about a CNN, you might have many layers, many feature layers. How do you decide which of those are significant? Is there a standard technique for doing that?
hmm, well, um, we have we have sets of techniques, and we really like the information theory within neural networks perspective. So while you're evaluating model within TensorLeap, so first of all, and it's a huge challenge, we need to rebuild the client model in our language, in our graph, in order to be able to head those hooks and listen to all the activation properly.
Mm-hmm.
So only convert it from ONX to friend H5 and protobuf and all those different kind of model formats to TensorLeap, it was a huge engineering challenge. But once you got to this point and you can listen to each mathematical operation, activation or response, you can measure entropy and mutual information and expressness between each one of those activation to the input to understand how specific it is, or to output and understand what the chances that this feature is actually contributing to a certain class prediction. Um, so
Mm-hmm.
we like those kind of techniques. We know that there is bunch of others, but
Right.
it's
And so would the
for
intuition be that for a particular class, there might be particular features that are very indicative, and then you would look for samples which didn't activate those particular features that would, for an explainability purpose.
yeah, yeah, and it might relate to the again to the reason we conducting those explainability. For example, we might come up and say, please explain to me why my data set is so redundant and why we have so much repetitive information. And there we'll probably utilize mostly features, indicators that can find features that good fit for duplication. And it's not necessarily you want to extract and distill latent space that capturing semantic information very well, but just we'll find features that can be sensitive to frame by frame kind of duplications if you working on videos and stuff like this. So
Mm-hmm.
utilize different kind of techniques and we'll try to extract features from the earliest area in the model. While if you're trying to detect overfit kind of features, you'd like to check not only if the model has high mutual information with the input and if the feature is very semantic and what is the depth of this feature and so on and so on. You'd like also to check if the model is actually uh, how well the model managed to generalize those features across the rest of the data sets, which is great.
Mm-hmm. Interesting. Right. And in practice, how does this all work? You mentioned that you would look over the entire data set to have an understanding. Can you give us a bit of a picture how that works?
Yeah, so let's imagine like autonomous vehicles companies, and they have few million samples, and you need to be able to, first of all, ahead understand which features are interesting, and then you need to conduct a certain kind of distillation techniques that is lean enough and quick enough that it won't take forever for you to build this embedding space for all those millions of samples, but also won't be too, uh, storage consumption. It won't take too much storage and you'll be able to save all this information, right? So basically, while you're evaluating, on the way, we're tracking after all the activation and conducting different kind of filters that focusing us on a few thousands, only a few thousands of activations. And from those techniques, we need to understand the mathematical operation way the way of mathematical operation generalizing its information. So we'll be able to reduce the dimensionality to something that we can save. So TensorFlow peacefully understands if those mathematical operation conducting some generalization on the spatial dimension or context dimension. So we understand if it's transformers, 3D conv, 2D conv, and there we conducting different distillation techniques for
Mm-hmm.
each one of those areas. And while we evaluate, we have our own kind of implementation for vector database because we started very early and we already built something that is very, customized to our needs, um, where we indexing all the information, all those activation for each one of the samples. And we have different processes that running in the same time that evaluating the model performance, extracting metadata from the input and indexing all the metrics that can indicate whether the model is failing or succeeding in those areas. So
Mm-hmm.
we like evaluation process usually takes the same time as it takes on the client. And we did a lot of infrastructure work to make it happen. But we ending with a huge data set databases that for each model that our clients evaluate for all the most important activation for each one of those samples, whether it's training set, validation set, all its unlabeled data per each one of the models they might achieve, and the huge documents databases that we can join with the features that describe the model performance per for each one of the samples and the object within the samples.
Mm-hmm. Really interesting. Since I guess you're looking at the features, that this technique or approach, these approaches are applicable to vision, language models, multimodal models. Is that correct?
Yeah, because for the system, it's once you manage to distill its information, you reducted the feature to one T or a few dimensions that describe the model, the feature expressions in the sample, we don't really care. It's tensor in and tensor out.
Mm-hmm.
Uh, you might analyze computational graphs or 3D models, time series, everything together. We have clients that working on time series with text and video simultaneously in one network.
Mm-hmm. That's really thorough introduction to the techniques. I'd like to dive into the engineering a little bit. You mentioned you had a infrastructure that you built to translate all the different model formats into a common format, and you also mentioned a custom vector database. Can you give us an overview of the architecture and what you needed to build?
Yeah. So if it's not enough that you need to maintain so many databases, microservices that can drill down and share computation properly and make everything in real time, we also have to be deployed on any kind of infrastructure. Many of our clients has no internet access. It's completely air-gapped. So we selected, we work in end-to-end in Kubernetes, and we build like those Kubernetes solutions that can apply on any Kubernetes cluster. And in cases we work on single machine, we squeeze this Kubernetes cluster into a tiny Docker. So we have a tiny Docker with Kubernetes within it, with all the databases and microservices, and it's all deployed exactly the same.
Mm-hmm.
Uh, and the thing we are deploying within this Kubernetes is, first of all, our infrastructure, which is kind of, we have three different solutions for queues, right? For each one of them has the right optimization for the velocity and the documents we're transferring. Um, it's kind of between Spark to Logstash and all those aggregators that taking the tensor results, reducting it and saving it in certain format that will be able to uh, it's kind of snapshot. So imagine that you have one process that inferring bunch of samples, generating lots of activation, some of the reduction happening in the main process and calculating metrics. And it's just dropping those tensor into Redis kind of implementation. And from there, we have a list of services that pulling those tensor, analyzing it a bit, and indexing it to the different databases. Everything in order to be able to evaluate and conduct all this computation without, you know, um, prolonging the evaluation and the training time too long.
Mm-hmm.
And it's all indexed to, first of all, snapshot in the memory, exactly in the way that our process that need to analyze its results will query it. So we have a very specific and unique kind of serializing those results into files and another caching system that caching those results, which is again, the snapshot from the model activation themselves. And this is how
Mm-hmm.
we set the information for each one of the samples from within the model. And in other places, we have our databases that, document databases, mainly Elasticsearch kind of things. We just about to consider to move to another kind of document databases. But yeah. And then this only the process that create the information. When the client playing with the system, the moment it gets to the dashboard, we have a microservices solutions that according to his action within the dashboard, we are pulling the relevant information. We're setting up different services that pulling and analyzing those activations, searching for correlation and bringing insight to the screen.
Mm-hmm.
Um, so for example, the moment you get into the dashboard, a process will come up, understand the model you're trying to analyze, pull all the activation from all the samples, from the snapshot to his memory, conduct a certain kind of dimension reductionality pipeline, clustering algorithm, search for groups, and then it will pull all the information from the document database, search for the cluster that tending to fail, project, you know, its model performance understanding on the model's most important features, information, search for all those insights and start to stream insight to the screen while it's while you play with the system. So it's everything in real time and everything is in
Right.
live.
Right. Sounds
Uh,
very, very complex, very modern, very interesting back end. I'm
yeah.
really interested to understand the product side, how you build a product around such a complex analytics engine, who the users are, different trade-offs you might make in terms of interfaces.
Yeah, maybe the product is one. While if the system and the tech is not deep enough, building products for data scientists to developing neural networks in any kind of domain and any kind of workflow, it's still, even comparing to the tech side, it's a huge challenge
Hmm.
because the people today, or at least till few years ago, didn't really had a proper paradigm and best practices. If you go to engineer, he like his Git, you know how you need to write pull request, how we have to request changes, how he's tracking his issues, how he's tracking his production environment. He knows everything, and you have there is one way to do that. If you're a good engineer, there is the good engineer way. And in data scientists, we are still building this road. Everyone is working in some path the first time, and no one know what is the best way to do that. And then to build a product, they're trying to iterate, integrate to a certain kind of development environment without understand the best practices. It just it's a huge challenge. But I think that we managed to solve it in a certain way so that like the thing we did is to be able to provide a system that you can integrate your own repository. You have this data loader that creating samples from anywhere and returning tensors, give us this data loader. And you have indicators, you have metrics, you have loss functions that get the tensor from the model, give us those functions. And we're building we wrap it, the model with those two interfaces. And this
Hmm.
is kind of all the integration. It took us a long time to get to the point you can support any kind of environment, any kind of Python environment, and so on and so
Hmm. Right.
on. And from there, the dashboard and the testing techniques, it's kind of, wishful thinking as data scientists that worked in the industry for the last 15 years. It's what I always wanted to have. I always wanted to have these testing procedures. I wanted to deploy a model after I know that it works well on all the edge cases. So I need a place to see test. I also like to to write code. I like to write C++ and to build a backend. And there I have hundreds of different tests that tells me that I'm okay. And when I'm not okay, I know exactly where and why. So it's kind of all the product is a wishful thinking of making data scientists scientific again, in the same best practices of development. So we have pull requests in TensorLib that you can come up and say, hey, this is the new changes I did in the data set. Those are the reasons. Those are the explainability technique that shows me that the model might fail in those areas. Those are the samples that I decided to label. This is the features that express in those samples that makes me believe that it will support the model failures on those specific thousands features. And then you're submitting a pull request to a friend with all those understanding, right? It's not like I used to be the one that deployed the most models in my previous company because I'm very compelling. I can convince someone that I'm right
Hmm.
only according to my intuition, but I were far from being the best data scientist then, right? But
Hmm.
it's what happens today. It's a lot relying on hunch and intuition and
Yeah. Yeah.
exactly.
So it's great to ground that in evidence, of course, and stakeholders often require, you know, uh, a convincing explanation that's grounded in common sense, I think.
Yeah,
Yeah.
completely.
Fantastic. Well, that's been a really fascinating introduction to the platform and the considerations behind the development of it. I want to end with one final thought. I'm just interested to ask you what you think are the big trends that are influencing the domain.
The domain of AI in general or
AI
explainability?
and explainable machine learning.
Hmm. Well, we feel like we saw so much of it, and it might make us feel that we already can find the trend and extrapolate and say what is the next steps. But I think that we are just in the beginning, and it's still so random. It's so hard to see what's going on. I have many friends that working on so many cool stuff from end-to-end human machine that works just amazingly to, different kind of physics theory generation that actually seems to work. So I have no idea. And even at my stage where I have a feeling that I understand this technology, I'm worried a bit. So I'm not putting lots of thoughts towards those direction, and I really think that it's gonna be almost impossible to understand what is the next, what's gonna be next with it.
Yeah, fair enough. I think even predicting 3 months ahead is a challenge, let alone
Yeah.
longer term extrapolation. But once again, thank you. If people want to follow on your updates and 10 sleep updates, which is the best platform?
To follow us, I guess LinkedIn, and we have a great hub on GitHub where we keep updating lots of different kind of work of project. We just take in some interesting data sets and latest models that answered it, and we building an end-to-end solution that shows how those model behave with TensorFlow, and I think that it looks super interesting.
Okay, fantastic. I'll drop the links in the show notes. Once again, thank you. Until next time, goodbye.
Roman, that's great.